The universal NAND gate. You remember that the NAND gate is an AND followed by an inverter. And the output of that is equal to A ANDed with B complemented. And this is the truth table for that. This here is another way to represent the NAND gate. It's the negative OR. If we put an A here and an inverter, the B here, an inverter into an OR gate, we get the same result because this one here is A bar ORed with B bar. The NAND gate is a universal gate. Why is it a universal gate? What does it mean to be a universal? It's self-sufficient. That means we can build any logic circuit with this gate. We do not need any other type of gates in order to implement any logic circuit. Only NAND gates. For example, the inverter can be implemented by the NAND gate this way, because here we have X ANDed with X, we get an X, inverted, we get an X bar. The AND gate can be implemented by two NANDs. This is the first NAND, followed by an inverter. Here the output is X dot Y bar, and here we take the complement of this, which will lead to this. The OR gate can be implemented this way. We have an inverter, and then an inverter, here we get X bar, and we have an AND gate here, the output of which is X or Y. Now let's see if we can implement this function using NAND gates. This function, by applying De Morgan's theorem, is equal to this function. Complement, complement. Notice that this function is put into the sum of product form. So if we complement it once, then we complement it twice, we have the same function, F3. If we take the first complement inside, what we get is this, ORed with this OR is converted into an AND with this term here, and the second complement stays outside. Now this part can be implemented using this NAND gate here. We have X, Y bar, and this is the output here, X, Y bar complemented, which is equal to this. And this part can be implemented using this NAND gate here. Okay, and the AND between them, we have this NAND here because of this inverter at the output. Now you notice that we have two levels of NAND gates. This is the first level, and this here is the second level. Okay, let's reanalyze the sum circuit to see if we get the same function. Okay, here the circuit is shown. Now the output of this NAND gate is, and the output of this NAND gate is, and the output of this NAND gate is this. Of course, this is equal to, take this complement inside, this will become an OR, and this will become this one, and this one will become this one. So it is the same function that we implemented. Now let's do the implementation in a different way. Given the function, notice that this is in this sum of product form. We can use the AND OR logic to implement this circuit, and we will get this circuit. Here we have an AND gate, and all the three parts here are ORed together to give me an F, which is actually this. Now, if we want to convert this circuit into a two-level NAND gate, we do the following. Notice again that this circuit is the same as this. Now, if we add an inverter here and an inverter here, nothing will change on the path because the signal will be inverted here. then inverted again. If we add an inverter here and an inverter here, nothing will change on the circuit. Also, if we add an inverter here and an inverter here, the circuit will stay the same. That means this circuit is the same as this. Now, this is a NAND gate, this is a NAND gate, and this is also a NAND gate. So this circuit is equivalent to this circuit. Notice that here we have E bar, which is this one. E followed by an inverter. This is an AND gate. So this is the two-level NAND gate representation of this function. So it is easy. If you have the function in the sum of product form, you convert it from the two-level AND OR logic into the two-level NAND gate logic. This here is another example. This is an AND OR logic. Add an inverter here, an inverter here, inverter here, an inverter here, you will get this circuit. And this circuit is two-level NAND gate because these are NAND gates, which are here, and this is an AND gate, which is here. Let's draw the logic diagram or the circuit for the function f, which has a domain x, y, z, using two-level NAND gates. The function is given as a k-map. Now we take we simplify the function from the map. Here we have a group of two minterms. This will result in this term, x, y bar. And here we have another group which will result in this term here, x bar, y. And this group, which is four minterms, will result in z. So we draw the logic for this one in the AND logic and OR logic. This is an AND gate, and they are followed by an OR gate. We add the inverter here, 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 and here, here, and here, and we get this circuit. This circuit is converted into this. This is an AND, the same thing. This is an AND, and here we have Z bar. If we take this inverter out, notice that here we have Z into an inverter. Here we have an input, a Z bar. And of course, this one here is an AND gate. Okay, if you were asked to implement this function using NAND gates only, how do you do that? First, you implement this function using AND OR logic. This is the implementation for this function using AND OR logic. Okay, here is the CD, the AND gate, which is this. Then we have the OR gate here, the output of which is this, which is here. And then the AND gate here, the output of which is this whole thing, which is this. And then all together ORed with BC bar. And this is the output F. Okay, how do we convert this into an NAND gate circuit? If we add an inverter at the input of the OR gate here, notice that we started from the output side, from the right-hand side of the circuit. We added an inverter here and an inverter here. Nothing has changed on the circuit. We add an inverter here with an inverter here, and then we go to this OR gate here. We add an inverter at the input and an inverter at the other end. We add an inverter here, an inverter here. So notice that this is an AND gate altogether with the inverter. This is an AND gate. This here is an AND gate. This here is an AND gate. And the last one here is an AND gate. And this circuit is equivalent to this circuit. You see here we have B into an inverter. I took the inverter out and I left it with B bar. And this is the equivalent circuit. This is a multi-level NAND implementation of the function. Let's take another example. Implement this function using NAND gates only. First, we implement it using AND OR gates. And you can verify for yourself that this is a circuit that represents this function. Now we start from the output side of the circuit to the first OR that we have here. We add here an inverter on this line. And then we add at the other input of the OR gate an inverter. So this is an inverter here. And we add an inverter here, an inverter here, an inverter here, an inverter here. We add an inverter here on this AND gate so that we make this one an AND gate. So this one is an AND, This one is an AND, this one is an AND, and this one is also an AND. So this circuit is equivalent to this circuit. Notice here, this NAND is this, and this NAND is this. This NAND here is this one. This inverter is added as an AND circuit. Of course, this has two inputs, not just one. Just to say that this is an inverter. You will also notice that C here on this circuit has an inverter, so we put C bar here instead of C, and D bar here has an inverter, so we put a D here instead of a D bar.